So far, we said, what if the circuit we're dealing with is not a circuit that has like sine wave or cosine as its sources? So what if you have like a general circuit and we wanted to solve the general circuit? So the idea is that instead of like solving it in frequency domain, we're going to take it to the Laplace domain, the Laplace transform of every single element that we have, along with all the sources that we have, and then we're going to treat all the elements just like a resistor, a favorite method to solve for the circuit. The idea was if I solve the circuit in S domain, in the Laplace domain, since there is a unique relationship between the time domain and the S domain, I can always convert the solution back to time domain, and I basically know the solution in time domain. Next time, we talked about how we can actually find the Laplace transform of every source that we have. Today, the plan is to talk about if I have like the solution, if I have the answer in the Laplace domain, how do I go back to time domain? Basically, how do I find Laplace inverse? Right? In the next lecture, we're going to talk about how we can transfer all the elements that we have to the S domain. And if we piece together all these components, we know exactly how to solve a circuit in S domain, right? Because we know exactly how to convert the sources, we know exactly how to convert the elements, how to go back to time. Right? So let's talk about how we can find the Laplace inverse. Let's just assume I have a function in S domain that looks like this. So assume h of s is a division two polynomials, g1 of s divided by g2 of s. Okay? The idea is that to find the inverse of such function. Right? So we would like to find inverse h of s, to call it h of t. Right? The first step to do that is to make sure this h of s is proper. The first step, make sure h of s is proper. To define a proper function to be a function that the numerator has smaller degree than the denominator. So when we're talking about like proper function, we're talking about the degree of the numerator. G is less than the degree of G2 of S. That is basically the definition of the proper. Right? If it's not proper, we can make it proper. Since the degree right? Extract the portion that's actually making this bigger, and the rest is going to be a proper function. Right? So I know exactly like how it's done. The second step, if I have an h of s, which is a division of two polynomials, I know exactly where the poles of this h of s are. Right? That's basically of G2. Right? Poles are, depending on if they're real or not, depending on if they're complex or not, you can break this h of s up to those poles. It's called partial fraction decomposition. So the idea is that break up h of s using partial fraction decomposition. And we know exactly how to do it in the poles, the types of the poles that we have. So given poles of h of s, we have three different cases. Case one, which means if I basically have the roots of G2, they're all distinct, all different poles. Right? So case one, there is repeated pole. Case two, it's when some of these poles are repeated. Okay? There are some repeated poles. The last case is, in addition to like case one and case two, I might have complex poles. Right? So case three, there are complex poles. So if I know how to take care of like these three cases, I know exactly how I can decompose my HFS into simpler terms, and then I can use the table and convert it back to time. Right? So step three is use the Laplace table to find inverse Laplace. Okay? The idea is that, like, how do I do this decomposition in each separate case? To start easy, let's look at the case one, where there is no repeated pole. Right? So case one is they're just different. For I can show this as this 2 of s its roots. So I can write it as s minus p1, s minus p2, to s minus pn. Still in GQ has a degree of n. I have separate roots. And they're all distinct. Right? It turns out I can decompose this function as follows. I can write it as a1 divided by s minus p1 plus o2 divided by s minus p2. S minus pn, where ai is the coefficient corresponding to the pole pi. Right? If I know what i's are, then I know exactly what my decomposition is. Right? One simple way that only works is that the common denominator here. Try to simplify it. Since this side must be the same as the left-hand side, I have to equate the denominators and find the coefficients. I can always do that. This works. But since this is a simple, very nice case, that all PIs are different, I'm a shortcut. Let's just say I want to find A1. Right? Let's just assume I want to find A1. Assume to find A1. Let's look at S minus P1. Remember, P1 is the pole corresponding to A1 times H of S. Right? If I do that, what happens to the right-hand side? Well, on the right-hand side, I have 1 times S minus P1 divided by S minus P1. So they cancel each other out. So I have A1 plus A2 times S minus P1 divided by S minus P2. A2 AM times S minus P1 divided by S minus Pn. Okay? Now if I look at the limit, when S goes to P1, S minus P1 is H of S. Here, constant, so I have A1. The limit 2 times S minus P1 divided by S minus P2. Then S goes to P1. This is 0, right? Why is it 0? Because the numerator is 0. The denominator is not 0. So I have divided by something 0. So the whole thing must be 0. Why is that 0? Because we have different. Therefore, P1 is not the same as P2. Right? So all these terms are actually 0. Right? There was nothing special about this A1. I could apply this for any AI, right? For any of these coefficients. I can basically look at the corresponding pole, extract that corresponding pole from the H of S, and find the limit. So in general, to get coefficient AI, which is corresponding to pole pi, is this goes to the pole pi minus pi times H of S. And as soon as I know exactly H of S is the into, so I can find H of T. Let's do an example. Example. Let's just say H of S is given to me by 2 times S plus 1 divided by S plus 2 times S plus 3. And the question is asking me, what is H of T? Okay. First step. Is this H of S proper or not? If it's proper, so it is proper. So H of S is proper. And then degree of G1 is 1, which is less than degree of G2, which is 2. Now this H of S is proper. Poles. The poles are degrees of the denominator. So it's -2 and -3. So I have poles. This equals -2 and -3. Okay. As soon as I know poles are, this H of S. If I look at the poles are different. So that's a repeated pole. So I know H of S can be written as some constant A1 divided by S plus 2 plus some A2 divided by S plus 3. Right? What we have to do is to find A1 and A2. And given this formula, now I can find A1. Find the minus P1 times H of S, which means this goes to this pole, -2. This plus 2 times H of S. Right? Which is, this goes to -2. This plus 2. This is my H of S. I'm going to plug it in here. Times 2S plus 1 divided by S plus 2 times S plus 3. Right? this s plus 2 and this s plus 2 cancel each other out. So this limit becomes a limit s goes to negative 2, 2 times s plus 1 divided by s plus 3. Right? And this limit is negative 2. Right? So that is my A1. I can do exactly the same thing for A2. A2 is limit s goes to third pole, which I know it's at negative 3. S pole, so that's plus 3 times h of s. H of s is this function. If I multiply h of s by s plus 2, this s plus 3, this s plus 3 cancels this s plus 3. So this limit is the limit of 2 times s plus 1 divided by s plus 2. Right? Which is 4. Right? Therefore, I know exactly what h of s is. H of s is A1, which is negative 2 divided by s plus 2 plus A2, which is 4 divided by s plus 3. Okay? If I look at the table, it's transform of the power of t negative AT is 1 plus 8. Right? Therefore, I can find the Laplace inverse. What is h of t? It's negative 2 the power of minus 2t t plus 4 times e to the power of minus 3t ut. Shortcut, we can find the constants. Done. And what do we have? So case 2. Repeated poles. Let me explain this by an example. Let's just say I'm given this f of s, which is s plus 6 divided by s times s plus 3, well, s plus 2 to the power of 3. Right? This is 2. Question is f of t. Right? Let's say I look at this function. It is indeed proper. Right? It's 4. Right? So f of s is proper. Yes. Well, I have a simple pole at 0. So I have a pole at 0, which is not repeated. So I can still whatever I had in case 1 for it. But I have one pole at negative 2, but it's repeated 3 times. So I have s equals negative 2, which is repeated 3 times. Right? Obviously, if I wanted to compare this, I'm going to have all the multiplications of s plus 2 to 3. So if I decompose it, f of s will look like some a1 divided by s plus a2 divided by s plus 2 plus a3 divided by s plus 2 to the power of 2 plus a3 divided by s plus 2 to the power of 3. Right? I have to have all those decompositions. Right? Because if I uncommon denominator, those little terms will show up. Right? The question is, how do I find A1, A2, A3, and A4. Let's look at A1. It's a simple one. Right? A1 is exactly like we had before. How do we find A1? Well, we're going to find A1. This goes to the pole, which is 0, times S minus P times f of s. This s and this s down here cancel each other out, so it's the limit. This goes to 0, s plus 6, divided by s plus 2 to the power of 3. So it's 6 over 8 or 3 over 4. That's simple, right? And the same logic as the case 1. If I multiply this f of s by s plus 2 to the power of 3, what do I get? I get times s plus 2 to the power of 3 divided by s, plus a2 times s plus 2 to the power of 3 divided by s plus 2, which is a2 times s plus 2 squared. For this term, I get a3 times s plus 2, and the last one is a4. Right? So if I find the limit, s goes to -2, all these terms become 0 by a4. Right? Everybody see it? So I can do that. So to find a4, I can use the same trick. A4 is limit, this goes to 2, s plus 2 cubed of s. This f of s over here, this s plus 2 cubed cancels this one. And I get this goes to -2, s plus 6 divided by s. Right? So it's -2. And let's just see for a second, we can use the same trick for A2 and A3. Let's look at, for example, A3. If I want to get A3 over here, I have to multiply this by s plus 2 squared, right? But let's see what happens if I multiply this by s plus 2 squared. If I multiply this term by s plus 2 squared, I still got no issues. With this one, I have still no issues. This one gives me A3. This one, I get A4 times s plus 2 squared divided by s plus 2 cubed, which is 4 divided by s plus 2. As soon as I find the limit, this goes to -2, this component goes to infinity. So I can use the same trick. With the exact same logic, I cannot use the same trick to find A2. Because if I multiply this by s plus 2, then these two terms go to infinity when I'm finding the limit. So what can I do? Let's multiply. Let's just say I want to find A3. Let's multiply everything by s plus 2 to the power of 3. Right? If I do that, so to find 3, I get A1 times s plus 2 to the power of 3 divided by s plus 2 times s plus 2 squared plus A3 times s plus 2 plus A4. That is basically s plus 2 squared f of s. Right? If I find the limit, when this goes to -2, what happens to this term? That is 0. I got no issues with this one. Right? That is 0. How about this term? That is 0. How about this term? That's the part I have issues with, right? So I want this guy and find the derivative of this guy. S equals -2. What's the derivative of s plus 2 with respect to s? It's 1. Therefore, this here is going to be A3. Since these two are greater than 1, derivative still has s plus 2 to some power. So when I'm finding this A4, if I find the derivative of it, that's 0. So if I look at the derivative of s plus 3 squared times f of s, that would be 3. So I know A3 is limit when s goes to -2 ds s plus 3 s plus 2 squared, right, times f of s. That's s plus 2 cube cancels this one. So I get limit s goes to -2 of s of s plus 6 divided by s. Right? How do I find the derivative of the division? Divided by v, v prime v, v prime v divided by v squared. Right? So if I do that, it's the limit s goes to -2. Is 1 times s minus derivative of the denominator, which is 1 times divided by s squared. Right? So that's basically -3/2. Right? I can use the same trick to find A2. This time I have to take derivative twice. Right? I have to take derivative twice to get rid of that s. And remember, if I have x squared, if I take derivative of this twice, I'm multiplying everything by 2. Right? So I have to divide it by 2. If it's like order 4, for example, to take derivative 4 times, so I have to divide it by 4 factorial, because it's 4 times 3 times 2. Right? So in this case, I want to find A2, and then A2 is s goes to -2, 2 factorial, s squared of s plus 2 cubed f of s. Which means I have to take derivative of this portion. Turns out this is -3. Right? Is it clear why I have like this 1/2 factorial? Remember, take derivative twice. When I'm taking derivative twice, for example, if I have x squared, the first derivative is 2x, the second derivative is 2. At 2. At 2, so I have to divide it by that. If I take derivative like 4 times, the coefficient is 4 factorial. Right? So I have to divide by that 4 factorial. Right? Now I have this function f of s. Well, f of s is a1, which is 3/4 over s, plus a2, which we found that to is 3/4, s plus 2, plus a3, which we found it to be -3/2, s plus 2 squared, plus a4, which is -2, s plus 2 cubed. At the table, e to the power of n factorial to the power of minus AT. This has the Laplace transform SA to the power of minus 1. Therefore, f of t, 3/4 is 3/4 t. This is 2t t. This one is a square. So then I multiply this by a t. So I have minus 3 halves t power of minus 2t t. And the last term is minus 2 divided by 2 factorial of t squared minus 2t ut. You guys remember, like, when we were talking about the differential equation, we said that if you have like a second order differential equation, if you have like a repeated root, we're going to multiply the solution by t. Right? And that's basically t that we're multiplying it out by. If we're solving like a third order differential equation and are going to repeat it, to get like the third equation, we're going to have to like multiply by t squared. That's how it's appearing in this equation. Okay? Does that make sense what we're doing? Yes? We're approaching this? Yes? Again, remember, we have to do this shortcut. We can always find a common denominator, set them like equal, and find the coefficients. You can always do that. The shortcut makes our life a little bit easier. Case 3, when there's a complex pole, it turns out there is no shortcut. We're going to have to go back to the old-fashioned way. Find a common denominator, solve for the constants. So case 3. Complex poles. And there is no shortcut. We have to find common denominator and equate numerators.
Example. Let's just say I'm given this f of s, which is 1 over s times s squared plus 2s plus 2. And the question is, what is f of t? Right? The very first thing we notice is that the degree of numerator is 0, the degree of denominator is 3. Therefore, this f of s is proper. Right? So we know f of s is proper. Therefore, we're going to look at the poles of this function f of s. What are the poles? Well, the poles are the roots of the denominator. Therefore, I have a pole at s equal 0. This guy. And I have poles at the roots of this s squared plus 2s plus 2. And poles at s squared plus 2s plus 2 equal to. If I solve it, the roots here are complex roots. Right? So I can't do anything. I don't have like any shortcut. I'm gonna have to like just try to do like the partial fraction decomposition and then try to find the coefficients. I know I can write f of s as some constant a1 divided by s plus I want to work with real numbers. So I'm not gonna basically decompose this into its root. So I'm gonna keep it as s squared plus 2s plus 2. But as soon as I keep like a second order down here, my numerator can go up to first degree, right? If the degree of the denominator here is 4, for example, the degree of numerator can go up to like 3. Why? Because we want to keep it proper, right? So I can write this as a2s plus a3, right? And this degree, the degree here is 1 less than denominator, right? The question is, how do I find A1, A2, and A3? Because as soon as I know what they are, I can basically look them up, and I know exactly like what these functions are in time domain, right? For A1, it's a case 1, right? It's a simple pole. It's not complex. It's not repeated. It's just a case 1. So I can compute A1 like very easily. So A1 is limit of s approaching the pole, which is 0, of s minus pole, which is 0, times f of s. If I do that, this s and this s cancel each other out. So I have limit s goes to 0 of 1 over s squared plus 2s plus 2, which is 1. Right? So this is the easy one. So I know my f of s is half over s plus a2s plus a3 divided by s squared plus 2s plus 2. Again, we do not have any other way but finding the common denominator and equate this f of s to this f of s, right? I know this must be the same as 1 over s times s squared plus 2s plus 2, right? We know that. So what is the common denominator here? Well, it is s times s squared plus 2s plus 2, right? What do I have for this one? I have half times s squared plus 2s plus 2. For this term here, I have to multiply it by s. So I have s times a2s plus a3. And I know this must be 1 over s times s squared plus 2s plus 2. Right? This term and this term cancel out. So all I have to do is to equate the numerators. So let's group them together. Let's put all the coefficients for s squared together, all the coefficients for s together, and all the constants together. If I do that, for s squared, what do I have? I have half over here. I also have a2 over here, plus a2. I got nothing else. For s, I have this coefficient, which is 1. And I also have a3s plus a3. And my constants, well, I only have like one constant. It is 1. And that must be 1. If these two are supposed to be the same, what does that tell me? It tells me this coefficient must be 0, and this coefficient must be 0. Right? So it tells me a2 plus half must be 0. Therefore, a2 is negative half. It tells me 1 plus a3 must be 0. Therefore, a3 must be negative 1. Right? Now I have everything. I can rewrite f of s f of s is half over s plus s squared plus 2s plus 2. A2s, it's negative half s minus 1. Right? I can pull this negative 1, basically times negative 1 out, and rewrite this as half over s negative half s plus 1 divided by s squared plus 2s. Right? This is easy. I know exactly what this is. This is a step function. This is the part that I got some issues with. Right? But keep that in mind. Just a quick reminder. If I have cosine AT UT, the Laplace transform of this function is s over s squared plus a squared. And if I have sine AT UT, Laplace transform of this is a divided by s squared plus a squared. Right? Looking at this looks kind of similar to these. They're not exactly. Right? But I can make him look like this. How? Remember, another reminder. If I have s plus a squared, I can write this as s squared plus 2 times as plus ac. I have this identity. And this looks a lot like this s squared plus 2s plus 2. So let's only focus on this and see how we can actually write this in terms of sine and cosine. So let's focus on that. So I have half s plus 1 divided by s squared plus 2s plus 2. Do you agree I can rewrite this as s squared plus 2s plus 1 plus 1? Right? And as soon as I do that, I know this term over here is s plus 1 squared. Right? How about the numerator? Do you agree I can write the numerator as half s plus half plus half? I can do that, right? So I can rewrite the whole thing over here as half s plus 1 divided by s plus 1 squared plus 1. I have this half left plus half s plus 1 squared plus 1. Right? Now it looks just like this, just shift it. I know if I shift in an s domain, it means in a time domain, I have to multiply it by exponential. So a reminder. If I have e to the power of minus at f of t, if we want to find the Laplace transform of this, the Laplace transform is f s plus a. It means it's shifted by a. Yes.
Like, I wrote that wrong. Is there still supposed to be a square on the bottom?
On the bottom? No. So this is squared.
I'm not seeing how it read. Oh, that's a plus sign. Sorry, I thought that was an equals within there.
Yes.
Yeah. But
Now we're done. Why? Because this is shifted by 1. So it's a cosine that is shifted by 1. So I have to like multiply this by e to the power of minus t. A over here is 1. Right? So if I want to find f of t, I'm going to write f of s one more time. F of s is half over s. We rewrote this as minus half s plus 1 divided by s plus 1 squared plus 1 plus half s plus 1 squared plus 1. Right? Like I said, this is very simple to write in time domain. This is a step function, so it's half step function t minus. Like I said, this is a cosine, but I know it's shifted by 1 in the s domain. So I have e to the power of minus t. I have 1/2 over here. Cosine a over here is also 1, tut. Right? Plus, this half is a constant. The rest is a sign. But since the s domain version of it is shifted by 1, so I have to multiply by e to the power of minus 1 times t sine t ut. Right? So that's it. So if the poles are complex, we have no choice but just doing the good old-fashioned way. Just finding the common denominator, try to find a constant just by equating the numerators. Right? Let me quickly talk about something else. If you guys remember, we said if I have like some input x of t, I can always feed this x of t to like some system, which is h of t, right? Let's just assume this system is very well behaved. It's an LTI system, right? And given that we can always compute the output y of t, which is the convolution of the input by the impulse response, right? But if you remember, this convolution was integral, so it's hard to compute it. Our solution was, instead of like solving it in time domain, let's just take it to the frequency domain. And in the frequency domain, this convolution becomes multiplication. But remember, the frequency domain is a special case of this, right? Therefore, I can take it to the S domain. And if I take it to the S domain, my output is still the multiplication. Given the fact that I know how to compute the inverse Laplace, I can always compute y of t. So I can take this, the S domain. My input becomes x of s. My impulse response becomes h of s. Right? What do we call this h of s? That was a transfer function, right? Because that's the ratio of output to input. So this is the transfer function. And then we can get y of s, which is x of s times h of s. Right? And remember, we can find like h of s from here. H of s is y of s divided by x of s. Right? And like I said, since we know the inverse Laplace transform, we can always compute y or any of these. Right? So let's do a quick example. So this is the property of convolution. Let's just say I have a system. I know it's an LTI system. I have input x of t, impulse response h of t, and the output y of t, where x of t is unit step function u of t, h of t is 10 times e to the power of minus 5t ut. Right? The question is, what is the output? Right? The very first approach is to find the convolution. I don't really have time, so I'm not gonna like compute the convolution, but I highly recommend you guys actually do the convolution at home. It's just the integral that you need to find. Let me quickly write it down and give you some hint as to how you can actually do this. So approach 1. We know y of t is x of t convolved with h of t. So I can write it as integral from negative infinity to infinity of 10 e to the power of minus 5 tau u tau times x of t minus tau, which is ut minus tau u tau. Right? That's the definition. All you have to do is you have to like make sure where these u tau and ut minus tau are 1 and find that interval, and then your integral is non-zero for that interval. Right? It's not a very hard thing to do. Right? Approach 2, however, is even simpler than that. We're going to go from time domain to the S domain. And we know in S domain, y of s is x of s times h of s. Right? Well, what is x of s? Well, x of s is the Laplace transform of ut, which we know is 1 over s. H of s is the Laplace transform of h of t, which is 10 over s plus 5. We know it from the table. Right? So what is y of s? Well, it is 10 times s times s plus 5. Right? I have to multiply out these two. Right? Now I know how to basically find y of t. How? I do the partial fraction decomposition. I know I can write h of s as some a1 divided by s plus a2 divided by s plus 5. This y of s is proper. I know the poles are happening at s equals 0 and s equals negative 5. Right? So this is the case 1. So I can compute a1 to be the limit when s goes to 0, s minus pole, which is 0, times y of s, which is limit s goes to 0. This s cancels this s, so I have 10 divided by s plus 5. So it is 2. A2 is limit when s goes to the pole, negative 5. S minus pole, so it's plus 5 times y of s. This s plus 5 cancels this s plus 5. So it is 10 over s, which is negative 2. Therefore, my y of s is a1 over s plus a2, which is negative 2, times s plus 5. Right? So I know exactly what y of t is. For this is 2 times u of t. For this one is negative 2 times e to the power of minus 5t ut. Right? Does that make sense what we're doing? Yes? So the whole idea is that we're going to have to do partial fraction decomposition. So we're gonna look at the poles, and depending on like what type of poles we have 3 different cases. If we're in case 1 and 2, life is good, we know the shortcut. If not, we're in case 3, we have complex pole.